Hey everybody, Nick with PMAS, Warren from Antilag Racing, Jeremy's off screen with Antilag Racing, and Scott and Rick here from FTY.
How's it going?
We're going to talk about airflow and restriction today and how they relate.
Awesome. So what do we have over here, Nick? You got a graph of some sort. What do we have on our y-axis and what's on our x-axis, so folks can kind of understand what this graph is about?
So the left side on this axis is restriction, or resistance to flow. The bottom is the actual airflow. Interchangeably, you can use airflow with horsepower. So the more horsepower that you're making with the engine, the more airflow that's going to be flowing through it. And what the gist of most of this is as you move more airflow through something, it creates more restriction. And what I'm going to talk about is how they relate.
Okay, so like if I wanted to move air through something like this, we can argue that it's going to be harder or take more energy or airflow to move through something that's got a smaller orifice compared to something that has a bigger hole in it. Would you agree with that?
Yeah, so that's what these two plots are. So to move air through something, you either need to push on or you need to pull on. You have to do a certain amount of work. So the more work you have to do to move the air through something, the more restriction is said that you have.
So that is what you're talking about as far as restriction that you're measuring in the unit of inches of water.
Inches of water is something that we use as the unit of measure for restriction.
Okay, so when a common term that we hear is 28 inches of water, that's a kind of an industry standard?
Yeah, so when you flow test something, as you see in this graph, we flow tested this piece that's in Warren's hand. It flows 500 CFM, it flows 750 CFM, it flows 1500 CFM.
So 500 CFM is here,
Yep.
1500 CFM is at this point.
Yep, and then how much it flows is dependent on how hard you pull or how hard you suck on the air through the part. That's the restriction. So if you're flowing two parts, if you can see that if you pull harder on the air, you're going to flow more. So how do you compare two parts, A to B? Well, you need to pick somewhere on this line of pull or restriction. Because when you flow through a flow stand, you need to pull on the air. So you need to pull on this two parts by the same amount to know that one moves more air at that same amount of suction. So somebody had to pick something like a unit of standard. So back in the day, a guy called Smokey Unick, who did a bunch of racing, who was testing cylinder heads and things like that, they had to pick something so you know this part flows more and this one flows less. So you need to pull on each part the same amount every time. So they picked it. It's 28 inches of suction, 28 inches of water, which happens to be -1 PSI, which makes a lot of sense for a lot of people. So you're pulling 1 PSI through a part and you pull all those parts through that same 1 PSI. Now you test this part and well, when I pulled 1 PSI, 500 CFM went through this. When I pulled 1 PSI through this part, 1000 CFM moved through that. So I know that part that moved 1000 is less restrictive. It flows more at the same. So when somebody says this part flows 1500 CFM, they mean it flows 1500 CFM at 28 inches of suction.
So that part could also move 3000 CFM, but
at
it would
60
be
inches
at
of
60
water
inches of water, which would be about 3 PSI?
Yeah. And it will also flow only 400 CFM, but it's only going to require 3 inches of suction to move 300 CFM. So a part, when you say it flows 1500, doesn't mean it only flows 1500. It just means that's the standard you used and how much it flowed at that.
And the big part that you're trying to illustrate with this graph is that it's not linear.
It's not the same, yeah. So that's why you have, diminishing returns. So what happens is these two parts, say if we tested these two parts at like 200 horsepower, 300 horsepower, the difference in restriction is resistance to flow and it costs you horsepower. So the more restriction something has, the more work the engine did just to move the air instead of spinning the crank and making power. So the more resistance to flow that you have, aka restriction, the more horsepower is wasted because you're using it to just move air instead of make power. So when you have two parts and you're only moving a little bit of air through them, the difference is small, right? So if you look, it only goes from like 2 inches of restriction to 4 inches of restriction, which in horsepower terms, it's like 1 horsepower, 2 horsepower.
So down here in between these two parts, for example, you've got 500 CFM through here. So that difference you're talking about is small from a restriction perspective.
Yeah, the difference in restriction is very, very little, which means the difference in horsepower loss is very, very little.
Now your graph over here talks about the inches of water that it was for that restriction, and you've correlated it into horsepower. Can you talk about that?
Yeah.
And how you calculated that?
Yeah, so what 2 inches of water is 0.07 psi. That's the only difference in restriction between those two parts at 500 CFM. Okay, so that means that there's very little power you're going to gain by going from one part to the other when you're only moving a little bit of air through that part.
Sure.
But what you notice about these lines is when you crank up the airflow, aka crank up the horsepower, the lines start separating.
Right. So if I go to the edge of your scale here, you got
It's like 1,000 horsepower.
1,000 horsepower in the air. These two lines have diverged completely.
Yeah, this one so far it's off the chart. So if we move back to say 900 horsepower, so now the difference between this one and this one is massive. So that one part at 900 horsepower, your restriction is only like 10 inches. Okay, so you only lost a little bit of power to moving the air. If you take that one with the screen in it and move 900 horsepower, your restriction's up here at 28 inches. So the difference between these parts in a horsepower number is about 35 horsepower. So if you're trying to move 200, 300 horsepower through these, and you take this one off and put this one on, you gain like 2 horsepower, whatever. If you're trying to move 900 horsepower, now stuff starts to matter, and you're gonna gain 35 horsepower by switching from this to this, because flow and restriction aren't a straight diagonal line. They
So it's
change.
not that that both of them didn't flow the same amount. It's just they flowed that 900 horsepower worth of air. Except one, it took a lot more energy, or what we're saying horsepower or airflow, to actually flow that number.
Yeah, so they both flowed 900 horsepower worth of air, or 1,400 CFM. They both flowed it, but the little one, you had to suck really hard on the air to get it moved through that part, and the engine has to do that sucking on the air, which we call pumping losses or pressure drop, okay? So when you have to pull on the air that hard, you use a whole bunch of horsepower just to move the air instead of spin the crankshaft. So that's why as you free up airflow, the car makes more or less horsepower. But the kicker here is the engine making 900 horsepower is moving the same amount of air through this, and one is gonna make 900 horsepower, and the other is gonna make 35 less than 900 horsepower, but they're moving the same air. So it's not like putting the bigger part made the engine move more air. It didn't. This didn't increase flow through the engine. What sets the flow through the engine is the size of the engine and how fast it's spinning. RPM and displacement sets the air. Putting a bigger intake or cold air intake on your car, or all these things, they don't move more air through the engine. The engine moves the same air no matter what, but freeing up restriction means that it had to use less suction to move that air. So when you free up the intake, you don't increase airflow through your engine. You just decrease the restriction it took to move that same airflow. A lot of people miss that.
If you were in a boosted application, you would see...
Now you're moving more air.
You would be less boost for that given amount?
So, yeah, so given the same 900 horsepower boosted engine, if you decrease restriction, it's still gonna make 900 horsepower, but it's now gonna do it at like 3 PSI less, because boost isn't a measure of flow. It's a measure of how hard you had to push on the air to move that flow. It's the same thing as I was just explaining, but in the inverse. So 900 horsepower of air is 900 horsepower of air. However you did, whatever you did to get that air through the engine, whether it was boost it or free up some other things, it's the same air.
So whether it was a big block Chevy, naturally aspirated, I'll make 900 horsepower. Or a four-cylinder at 50 pounds of boost, making 900.
Yeah, a good analogy is like using like an old roots blower, right? So I have a 454 Chevy and it makes 1,000 horsepower, and I have this big roots blower on it, and it made 1,000 horsepower at 5 PSI. Say it's a really big roots blower. Say it made 1,000 horsepower at 5 PSI, and I put it, that same blower, spinning the same speed off the crank, put on an engine half the size, okay? It would still make that same exact 1,000 horsepower, but now it would be doing it at 10 PSI because you had to force twice as hard on the air to fit in an engine half the size. But the air is the same, which means the horsepower is the same. The boost just changed because you're shoving the air in a smaller hole. And to put twice the air in the same size hole, you need to pack twice as much air or double the boost.
So what you're basically saying is, here's your big block Chevy.
And here's a small block Chevy. Yep, so
Effectively
you
what
can
you
make the
said.
same power, but you gotta shove twice as hard on the air, boosted, or in the inverse, you gotta pull twice as hard on it to get the air to move through the same hole. So it's the same thing, but people miss that a lot. They think that airflow is like something, and that like, if I say this part flows 1,500, it gets to 1,500 and there's some magical force that stops 1,501 from going through the part. And it doesn't work that way. It's not a flow restrictor. It'll flow 3,000. You just got to shove twice as hard in the air. But when people hear 1,500, they think that that's the end. No, that's just when it hit 28, which is a magic number that Smoke Unit picked. So you had the baseline and compare everything together on the same playing field.
So to reel everything in, this graph, we're looking at restriction. There's a measurable amount of horsepower that's associated with that given restriction.
Yep, cost horsepower.
And the way that it behaves as flow increases is not linear.
Correct.
It is on a curve.
Right, which is why, even though the parts they might have a small difference at a small flow, when you start cranking the power through something or you're moving a lot of air through a little hole, now stuff starts to matter. Where you change at a 900 horsepower, you change from this part to this part, you may be picking 50 horsepower up. Where if you put it on your NA Honda that makes 200 and you change it, you might gain 5. So it matters, and it's not a linear thing. So, and it also works in the inverse with laws of diminishing returns. If you have a 5-inch intake on a car that really needs a 3, you've picked up all the horsepower there is. And you go from a 5-inch intake from a 2, maybe pick up 20 horsepower. If you go from a 5 to a 10, it might only gain you another half a horsepower because your curve is running out. You're having diminishing returns because you're getting so far to where you're going this way. So as you start getting closer, the difference between the two things gets smaller and smaller and smaller, and pretty soon it's not worth trying to package a 12-inch intake in your engine compartment. So you weigh that.
Or if you're going with a small throttle body versus a larger throttle body.
Yeah, same thing. If it's so far oversized that it's not making a difference anymore, then was it really worth it for all the hassle of putting the parts on? So there's always extremes. You can't fit a 12-inch intake in your engine compartment. If you could, if you wanted to, and it would make technically more horsepower than a 4-inch.
Well, I mean, now they put like turbos and stuff out of the hoods and all kinds of other things. So
it's just how much crap you want to deal with for that last little horsepower, and that's everybody's personal choice of what they want to spend or what they want to fab for every little last piece. But the biggest thing is remembering that every flow has a restriction associated with it when you're moving air through something. And when someone says it flows 1,500, it also flows 2,000, but it also flows 400. Someone says, oh, I don't need that part, it flows 1,500 CFM, my engine only moves 500. Well, that part, it also flows 500. It doesn't have to flow 15. So here's that. So you say you pick this part because it has this big gap, but your engine only makes 400. Why do I need this part? Well, it still has less restriction, even down to 4 horsepower. It has less difference, but there's still a difference, even though this part for 1,500 or was rated for 1,500. And you're only flowing 500, it still makes a difference and it helps.
And we're in an industry where we're trying to squeeze as much horsepower out of something, right? So if you're going to gain 5 horsepower based on a restriction,
especially if you can fix it for $100 or something like that.
Why wouldn't you do that?
Yep, it's worth 5 horsepower for $100.
Awesome.
So
all I'm hearing is go for the 12-inch intake.
Yeah.
I agree.
Everybody else, there's other people in this room either sitting by, make sure you don't say anything really stupid, but anybody else.
What, like that? Oh, okay.
Yeah.
It's just about improving efficiency of your air pump, right?
Yeah, because engines are air pumps, and everything
you do improves the efficiency of it to remove the restriction.
Yep, and any work it has to do to move the air instead of spin the crank is horsepower you lost to pumping losses. They call it pumping losses because it's what you lost to move the air. And it takes horsepower to move the piston up and down, especially if you're trying to pull against a suction, which is a restriction, where that piston's trying to come down and it can't suck in the air and fill the cylinder. It's working against that. It takes horsepower to pull the piston down because you're trying to pull air. If everything's free and open and there was no cylinder head on it, the piston would just come down and there's no work to be done.
So something like this could also be seen in your volumetric efficiency table?
It's the same thing. Yep, it's the VE tells you the efficiency the cylinder was filled, and that is taking into account the valve size and the ports and all this other stuff going on, but it's still the same thing. It tells you how well you've effectively filled your engine full of air. And if your displacement is 300 and you happen to fit 300 worth of air, your VE is 100%. Anything less than that means you didn't move all the air in there. And usually the VE will correspond with restriction, because restriction is what causes the VE to be lower than 100%.
Which is why your VE isn't 100% at idle, because you have a throttle body restricting the flow.
Yeah. Your VE is like,
because otherwise
5.
the VE table would just be 100.
Yes.
Yeah. And yeah.
And why diesels are so efficient, because there's no throttle blade, and they run ridiculously good VEs all the time at part throttle and low loads, because there's no throttle blade working against the air. On top of the fact they run a lot leaner. They run as lean as humanly possible all the time. But that's what helps diesels. There's no throttle. There is now for emission stuff, but for all intents and purposes, diesels don't need a throttle brake. And that's why, that's why the
That's
VE,
interesting.
VE on diesels is really high, because you don't need to block the air to keep the RPM down to make it on the idle instead of free revving. The fuel does that. You just give it less fuel because it runs on the ragged edge of lean all the time. I didn't know you didn't know that. Look at that.
know
Warren
that.
even
I
learned
learned
something today,
something.
too.
You have a diesel. You have
a
two
diesel.
diesels.
Two diesels, yeah, just know that.
Wow.
It's just sorcery, and fuel goes in
Gotta
and
learn
magic
something
comes
new.
out. Yeah, cool. So, a little short lesson for today. Try not to get too in this, and keep in mind, people, I know there's some people that are gonna watch this video and be like, yeah, you're not talking about wetted perimeter and all these other things. I get how those things work. A lot of us in the room do, but this video isn't to teach us something. We kind of get how this stuff works. We want everybody to understand how fluids work and how flow works and how resistance, and we're trying to explain in a way that everybody gets it, and you can associate it to things you've experienced yourself personally.
The biggest part too is that a restriction has a horsepower related loss or gain with it. And how you can correlate that in your system is important. You're basically talking about twice the flow, 4 times the restriction.
Yeah.
Is that your general rule of thumb for stuff?
That's pretty close. Yeah, so if you double the flow through something, through most shapes, you're going to quadruple the restriction. So that's a pretty good, which also means you're going to quadruple the horsepower loss through the part, that's lost to. And the other thing that people miss on cold air intakes, and that what's done that is the term cold air intake. Everybody thinks they add a cold air intake to get colder air. Before that term got coined, and I think it was way back in the
Misused.
90s with Honda boys back in the day calling everything cold air intake. I think they came up with that term. But you built your intake to have less restriction, not colder air. The big thing, because most of those intakes back in the day were very restrictive, they were designed to make what the car does stock, and that's it, no other room. So you change your intake to a bigger, freer flowing one to have less restriction. The cold air part was just kind of a side effect thing, that if you could get cooler air, it's going to be more dense, you'll make more power. But the reason people were designing aftermarket intakes was to decrease
Yeah.
restriction, not make the air colder. So now everybody's like, oh, my car doesn't, this cold air is fine, it pulls it from the back bumper to get my cold air. Well, you forgot that you added 12 feet of pipe, and anything you gained from cooler air, you lost because you added a bunch of restriction in a 12-foot long pipe.
So basically, if I put a pipe that's this big
Yes.
to the back of my car,
That's-
even though it's a 6-inch pipe.
Yeah. That's
Just-
probably big enough that it wouldn't matter if it was 12 feet long.
Oh, okay, never mind.
If it was a 3-inch pipe, it'd
Home
matter.
Depot racing.
So infrastructure might come into
Anyway,
play.
so yeah, so that's why that term cold air intake kind of bothers me, because don't forget, you're decreasing restriction too. It's not just about getting cold air. You've lost a bunch of power. Most of the OEMs I see design their stock intakes to have about 28 inches at whatever the car makes stock. General Motors usually designs for that, at least what I've seen in testing and feedback I've gotten from engineers there. And Ford, they usually design for about -1 PSI of restriction at whatever the car makes for horsepower. So that means you've left 1 PSI on the table, and everybody that's got a turbo knows you turn it up 1 PSI, you're going to gain some power. So if your stock intake is -1, and you can put one on it that's -0, that's horsepower we made. It has nothing to do with the temperature of the air.
It's like turning up 1 pound of boost to air.
It's literally the same
Yeah,
thing.
It's literally the
I
same
mean, we
thing.
can't get 0 restriction on an intake unless
Right.
you built a 6-inch, which practically on a Honda, and you can't fit that in the car. So, but within reason, yeah, you like the ones that we make for Coyotes, they're like 5 inches at 500 horsepower compared to 28 stock. That's why we picked up 12, 15 horsepower, and the math tracks that.
Mhm.
So Ford engineers and GM engineers, they have design constraints, right? They have to deal with noise, and the car has to run in the desert full of sand, and when it's 120 and it's -30.
And it has to be cheap,
It has to
too.
be quiet so that Granny doesn't start her car and she's like, this thing sounds like crap. So we don't have a lot of those constraints in the aftermarket, so we can make more power than the OEMs do with their stock stuff sometimes, because we don't have to follow the same rules that they do when they build stuff. Cool.
Great. Thanks.
Yeah.
Appreciate it, man.
Yeah. All right, guys. Make sure you like, share, and follow the page. We should have lots of good technical stuff coming forward too.
Cool. Thanks for sharing. And cut.
Do you say cut?
You do what you say, whatever you want. Yeah.
Should leave that part in.